Welcome back to my Commodore 64 Games Memories video series. This is where I look at old games and some of the technical details behind them. Today we have Encounter, published in 1984 by NovaGen. Creator was Paul Wokes. We're going to have a quick little look at the tape turbo loader, then see how the game uses multiple character sets, double buffered screens, with screen mirroring, and also trying to make some of the demo games playable. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are all always very much appreciated. I think I had the original tape version of this back in the day when I must have been, 12 or 13 years old. This game kind of reminds me a little bit like Battlezone. Battlezone in the arcade was a 3D vector type of game, and I used to play it quite a lot, especially when we went camping and things like that, or at the seaside in the amusement arcades. So these are just the instructions for different versions of the game, but let's start with the tape turbo loader. So the initial load for the tape turbo loader does not auto start. We can see here that in the memory used for the tape header, that there's just the file name and the load address and everything like that. The rest of it is filled with space. It seems to be loading at the start of basic memory what looks like some basic code, and then it's got what looks like a sys2423 in there, and then there's some machine code after that. So there we go, there's the basic program. We can see that it's 13 times 496 is 53248, and then plus 32 and plus 33 is 53280 and 53281. So that's just setting up the border and the screen color. It's then doing some prints to clear the screen and move the cursor around and display this message. And then at the end, it's doing sys2423. So when I was very young, and I was just starting to get into assembly language programming and machine code stuff at the tender age of 11, 12 or 13 years old, I found this on the tape, and I was really, very intrigued about how it was actually loading information from the tape. And this actually led me to understand tape turbo loaders a lot better. So I'm just warping through the loader here. That's why the emulation has sped up. We can see it's loading a whole bunch of stuff. There's quite interesting wobbly sound effects, right, as this loads from tape. I thought that there was quite a good deal of variation. I also really like the blocks to load display. Some games used to do this, but this was the first game really, I think, that stuck in my memory anyway, that's what it was doing. So this code is a little bit unusual. If we step through this code here, then there seems to be this tight loop of loading X with A, B and 0 page, and then branch not equal. So that seems to be a flag. And then when it's loading data, the data byte seems to be coming in on the 0 page memory location AA. But if we have a look at the CPU history, actually that tight loop is exited by this interrupt coming along. The interrupt goes through the standard kernel vector, and then it goes through the extended 0 page kernel vector for the default RQ vector, which is at 314 in hex. The code is basically, when it starts, it ends up at A89 in hex, and then it does a load with the high byte value of one of the timers. It's then acknowledging the timer and restarting it by storing into DCOE, of course. It's doing an EOR and a couple of shifts to actually get the bit that we're interested in, based on the high byte of the timer value. So yeah, there's the timer control there. Yeah, so it's definitely restarting the timer, and it's loading the start value into the timer again. Yep, cool. That's at A8C there, but yeah, this is kind of like standard-ish. The interesting thing to note here is that it's got a deck with A9 at A97 here. So if you watch my previous video on tape turbo loaders, mostly tape turbo loaders seem to use a bit shift pattern, where a bit is shifted off the least or most significant bit using the rotate instruction, then that signifies that the whole byte has been read. But in this case, this tape turbo loader is a bit unusual in that it's actually counting the bits rather than reusing the register with an end either set or cleared bit to indicate that the byte's actually being completely loaded from tape. So this tape turbo loader, because it counts the bits, once it has finished counting all 8 bits, then it stores 7 back into A9 there at A9F in hex. Otherwise, it does a branch on plus which to A80, which basically exits the IRQ again. So we know here now that, well, the shifted byte that's loaded from tape is in AE, but it stores it into AA, and then it flags AB to indicate that the mainline code should process the byte that's just been loaded. So this makes this tape turbo loader unusual in that the work is split between the interrupt, the IRQ, and the mainline code. Instead of doing all of the work in the interrupt and then the mainline just waiting for a flag to say loading is complete. So a slightly unusual way of writing this tape turbo loader, but it's a relatively robust way of doing it. So I'm going to be updating my debugging notes text file with all of these findings, of course, and committing it to source control in my GitHub. And I will put a link to that file in the video description below, so you can also follow along with these debugging notes. So here we are back in the mainline. Now, mainline code is what I call code that is not executing in the interrupt. It's the main part of the code, the mainline execution code. So we can see here that this code goes through some various states, and it looks for a sync byte of AA. It then processes probably a start address, and then it's doing this indirected store. Now, this indirected store with AC, Y then stores all of the bytes that you would expect when it loads using the tape turbo load routine. But basically, we have this little subroutine there at A42, and it's doing repeated JSRs to A42, and A42 is the routine which gets the completed loaded byte from the interrupt. So it's not a state machine. It's just basically code which runs through, which is different to a state machine and different to the kind of tape turbo loader style of code that we normally see in games, where games use some kind of like state machine and then the interrupt processes the loaded byte. So we can see, if we're looking at the actual tap file in the hex editor, we can see the expected bytes, because AA in hex, if we convert hex to binary, we can see it's a repeating pattern of 10, 10, 10, 10, and we can see the expected bit pattern here, which is 10, 10, 10, 10, but it's probably the opposite way around because it was doing a rotate right rather than a rotate left. Whatever it is, we can see that that's the pattern that we can see in the tape loader. So we can see a whole bunch of shorter pulses to begin with. Those are the 2, 7 values there, and then 5, 6 seems to be the longer pulse value. So this is why tape or tap files are useful, because we can actually see the timing between the pulses and we can match that up with what we see in the code. When a loaded byte is stored into memory, it seems to do a rolling checksum into AF. There seems to be a checksum every 256 bytes. So this seems to be a block-based loader for this tape turbo loader. So actually it's doing a little bit of a more robust check, if you like. A lot of games seem to do a checksum for the whole file, but this seems to be doing a checksum just for 256 byte blocks. So I think that's more robust. Some of my tape turbo loaders, when they do block load or when they do compressed block load, they also have a checksum per 256 byte block. 256 bytes, of course, is just because it's 2 raised to the power of 8, which is just a nice round number if you're doing binary computer stuff. So right down towards the end of the load, the tape turbo loader then goes through, and then it does this indirected jump with AC and AD being the 0-page memory locations, which then indirect to 9C00, which is the start of the code. In theory, we could save out the whole block of memory and then compress it, and then probably create a nice compressed executable PRG file from that, but I don't think we'll bother making a compressed PRG file of this. We'll just let the game run, I think. Here we are in the game's title screen. So the title screen is nice and functional for 1984. It's got a nice defined character set, and all of the instructions are on the title screen. You press F5 and F7 for the difficulty and F7 to begin the game. I think if you leave it on the title screen, the game goes into like a demo mode. There's a little typo in the instructions. Look, instead of start, it says stars game. Whoops. I'm surprised I never noticed that before. So let's let the game continue on now, and hopefully go into the self-playing demo mode for this game. Here we are, it goes into the self-playing demo mode, which is really quite useful because then I don't need to worry about controlling it and also pointing out interesting things on the screen. And also it's doing some firing and, well, shooting and stuff like that, which helps. So we can see, actually, that there is a ton of memory being updated there with the green and yellow blocks. Wow, there's quite a large amount of data being read and then written. Writes are yellow. Blue is code execution, green is reading from memory. We can see that we've got at least two different screens there at 6000 and 6400 for the game. We seem to have several character sets being used. So character set 58 seems to be the bottom part of the right hand screen. If I advance each frame in the emulation, so I've paused it, I'm doing the frame advance function now, I can see that it seems to be taking maybe 2 frames, is it, to actually render one screen? So there seems to be 4 character sets. Look, one at 4000, 3800 is the other Vic bank, so it's not going to be using that one at all, right? So 4000 seems to be the top of the screen, at least. Let's have a look for character sets. We go into the second. Yes, look, we've got 4 copies, at least 4 character sets, maybe even 5. Look, there's a character set down at the bottom of that Vic bank as well. Gosh, okay. So we have 4 character sets at the beginning of the Vic bank, taking up basically half of the whole Vic bank. And character sets are actually dynamic as well, so you can see those dynamic characters being updated. Now, it's interesting that this game is continuously updating the character set information. So we have other characters where we've got, let's go back to the ROM characters. So we can see that the ROM characters, look, the empty space for the sky seems to be at, which is the 0 character in terms of ROM characters. We seem to have the whole bottom of the screen there as well, using a different character set. So maybe the character set at the end of that Vic bank is being used for the score panel as well. Right, okay, so character set 4000 and character set 4800 seem to be the top and bottom parts of the left-hand screen. And then character set 5000 and character set 5800 seem to be for the top and bottom parts of the right-hand double buffered screen, so the second double buffered screen. So this game makes extensive use of character sets. The more that's on the screen, actually, the more information seems to be put into the dynamic character sets as well, which makes sense, right? Because most of the display seems to be using characters. There do seem to be areas of the screen that are rendered with sprites as well. Let's just double check where the sprites are. Yeah, so look, we can see that there's some mountains, maybe some explosions, clouds, definitely. Okay, but yeah, the mountains in the far distance, look, and then we've got the clouds up at the top of the screen as well. But yeah, we can see the more stuff that goes on the screen, the more, I think, the more information that appears inside the character set. So let's go to the character set at the there we go. There's the character set at the end of the Vic Bank, and that's used for the title screen and also the bottom part and also the top part of the screen as well. So we've got the score up at the top of the screen, and we've got the status panel and everything at the bottom of the screen. So that's the character set that appears right at the end of the Vic Bank too. So that means that we have a couple of what is it? 1, 2, 3 screen splits at least between different character sets. One for the score panel up at the top, and then the transition to the game top part of the game screen, and then the horizon is the second character set at least, and then there's the same character set at the end of the Big Bang for the score status panel down at the bottom of the screen. I'm just adding some notes to the debugging notes text file, which I will of course commit to source control. I have a crazy idea. Let's fill the character set information for the game display. Anyway, let's fill all of those character sets with 0. So the end of the character set data for the 4 character sets is 4000 to 5FF, and we fill that with 0. Now you can see, as we move around, we can see exactly in the graphics map view there, we can see how the dynamic characters are added to the character set. Now what's interesting to note is that some of the solid areas actually in the game view aren't updating properly, and that's probably because, so it's not because I filled it with the wrong character. I think that kind of like indicates to me that there is some kind of like caching mechanism, perhaps, or maybe it's just initialized some of the character set information before the game actually starts, and then it doesn't render into them again because it needs to know that it has a solid clear character, a solid black character, maybe the multicolor 1 and 2 characters as well. Let's see if we can get those restored. So I have a hunch. Let's go back to the title screen, and then let's go back into the game itself. Well, let's let the demo mode start going. So let's clear the character set while it's on the title screen. So we've done the same character set clear. You can see that the 4 character set, there we go. The game is now back again. So yeah, I think it's either like a caching mechanism, or it just initialized those characters once for the solid filled colors, or maybe the solid blank character as well, and it just didn't reinitialize it during the game. It's just initialized it once from the transition from the title screen to the actual game itself. That's useful to know. So let's add a watch store for arranged memory range here. So we'll just look for stores into the first double buffered screen bank. We'll try and find the code which stores into the top part of the screen there. We'll reduce the range a little bit so it's not going into the bottom part of the screen. So hopefully it's just into the top part there. Let's see if we can get any sensible code. So this looks like it's a clear loop. Okay, so let's get rid of the ranged watch point for that memory store there, and then we'll just put a breakpoint after the clear, and then we'll restore the ranged breakpoint store there. There we go. Let's see what we've got now. So I think if I go back to the ROM character set, it's not a ranged watch point for the whole of the top of the screen. So I think we're probably, there we go. Let's hop out. Oh, look, there's a whole series of JSRs starting at A103. Well, this kind of like indicates to me that maybe this is the main game draw loop, right? This is why we use ranged watch store points and then hop out to the parent routines in the monitor debugging windows here, so that we can actually try and locate these kind of like program structures. So most programs are structured in a way which hopefully makes them easier to understand or easier to develop, right? So you would normally find some kind of structure in a game where, say for example, we've got a load with D012, which is the raster position. That's for synchronizing screen updates to the raster position on the screen. We have a whole bunch of JSRs in a row, which indicates that this is structured in such a way as that it does like a draw or setup routine or calculation. We'll get into those in a bit shortly. So let's put a break on A103. There we go. There's the start of the JSRs. Let's put a breakpoint after each JSR and on the compare, which is to the exit of that JSR, and see what happens on the debug graphics map, right? So we seem to have a clear part of the screen on the second double buffered screen already. It's cleared with @. Starting from the title screen, let's ensure that we've got a nice clear few double buffered, well, let's clear the character set information so we've got a blank character set. So we can see when we jump over or when we allow those JSRs to be executed at A103 onwards, there we go, we can see what happens. So we can see immediately on the transition from the title screen to the start of what looks like the game draw loop, right? That even before the first iteration of the game draw loop, we have these characters. We've got 4 characters, a blank one, a multicolor color 1 character, multicolor 2 character, and then the actual solid filled character as well. So that's useful to know. We know that the 4 character sets are set up with these solid and 1 empty character or a clear character. So we'll put that note into the debugging notes text file. It's important to note that because this is kind of like the setup that was done of the character set data at game start. So the top of the second double buffered screen seems to be clear already. I think this is partially displaying the previous screen from the previous iteration of the game loop, I think. But basically, if I hop over that now, we can start seeing that it's doing some calculation, perhaps. Now it's drawn into the character set and it's drawn into this top part of the screen. It's then updated the bottom part of the screen for the second double buffered screen. If we continue on, this is the second iteration through the loop now. And the first part of the double buffered screen up at the top has been cleared now. And this is the second iteration of the game loop. And we can see now that if we continue on now, then the second character set has already been rendered into, and that's because it's used for the second double buffered screen. But if I continue over this JSR now, so we'll just continue the execution, and we'll continue execution to the next JSR at A106. But yeah, the top half of the screen, right? Let's not, what shall I do here? Just making sure that, yeah, this does seem to be the start of the draw loop, right, in the code. So let's go to the next JSR. Okay, so that was just doing, I think that there's a whole bunch of calculation being done because I don't see anything rendered into the first screen, into the top half of the screen anyway, and I don't see anything rendered into the first couple of character sets either. That's the next draw. It's not a draw, it looks like calculation. That looks like a draw, yep. So the previous JSR at A109 has drawn at least into the top character set and the top half of the screen. And then this next JSR at A10C probably will do a bottom of the screen draw in the character set, right? So that's the calculate into the top character set and drawing the top part of the screen there. And then it's interesting to note that the bottom part of the screen has not been cleared. If, as I suspect, the bottom part of the screen is a mirror of the top, then there's no point in doing a clear because you're going to be mirroring what's in the top part of the screen anyway. So let's have a look. A10C, yeah, okay, so it has already drawn now into the second character set and then updated the bottom part of the screen as well. So just updating the debugging notes text file here. with these findings so I don't forget what it's doing later on. So back in the title screen, let's clear the double buffered screen, both double buffered screens. Okay, so let's fill all of this memory for the two screens with 0, and then we'll see exactly what, should we fill it with 0 or FF? We'll fill it with 0. It's you know, pros and cons about whatever character I fill it with. It just makes it probably easier to understand. So let's put a break at the beginning of that draw loop as well. We'll put the range breakpoint in there, so we don't need to keep on clicking. There we go. Right, so, well, that's changed the bottom of the screen for the score panel. Whoops. I don't really care about the score panel being corrupted now, because I'm just concentrating on the game code. So let's go back into the title screen and clear the character set information and also the double buffered characters. Double buffered screens, which contains the characters for the screens. Then we'll put a breakpoint there at the start of the draw loop. Then we'll go back into the game. Right, okay, now we've got a cleared character set, which just contains those solid characters with the multicolors and everything else. And now we've got cleared screens. Now we can step over each of these JSRs and we can see exactly what's drawn into memory. So A109 should draw the, the top part of the memory and the top character set. So we'll hop over that A109 now by continuing the execution, right? It should just draw the top. Verify that. And there we go. The top part of the first double buffered screen has been drawn into with the character set updated. A109, so A10C should draw the bottom part of the screen. We'll do a ranged store breakpoint for the screen data, and we'll see what the bottom part screen render does. And oh look, the bottom part screen render is loading from the top part of the screen, EORing it with FF, and then storing it into the bottom part of the screen. Well, that's funny, isn't it? So yeah, that definitely confirms actually that the bottom part of the screen render is doing a mirror of the top half of the screen, but also EORing it with FF. So it's using a different character range in the character set between the top and bottom parts of the screen. So that's why for the bottom part of the screen, it looked like it was filled with FF in the bottom landscape part of the screen compared to the top half of the screen, which was filled with apt characters, which is 0. So yeah, the bottom part of the screen is a lot simpler and cheaper to render into. That's why it doesn't bother doing a clear of the bottom part of the screen, because it always knows that it's doing a mirror of whatever is in the top part of the screen, which is cool. It's a semi-unrolled loop as well. It's not fully unrolled because that would be huge, but it's basically mirroring each screen row, which is the 40 characters across, or characters 0 to 27 in hex. That's why we have that load X with $27 in there. So let's see if we can do a ranged watch store point for the screen render now. We'll just put some extra breakpoints in there for the execution as well. We'll just hop over them. Doesn't seem to be doing anything for the score update into the top part of the screen in these JSRs anyway. We're just looking for the screen calculation now, and there we go. This is the top part of the screen calculation, and it's a lot more complex than just doing a mirror, of course. It's actually doing quite a lot of more complex code. There's shifts, rotates in there. It seems to be loading from somewhere in memory and then doing an indirected store. This kind of looks like a lot more complex block drawing code, right? So I expect this game is storing the block definitions, the object definitions as block data or ranges of bytes or whatever that needs to get stored into the screen, plus also the character set definitions for them as well, I expect, maybe, possibly. But yeah, the top part of the screen is a lot more complex than the bottom part of the screen. I just noticed I tried to do a soft reset and it's come back to the title screen. doing more soft resets. It's coming back to the title screen. Ah, it's got a CBM80 up at 8000 in hex. That's just, you know, like a warm start reset claiming piece of magic bytecode there, which is quite unusual to find in the game. But it means that you couldn't reset this on a Commodore 64. It thinks that there is a ROM at 8000 in hex. It's not, it's just that the data is in memory. And a warm restart, a warm reset on the Commodore 64 doesn't clear that memory. So the disk version of the game actually has a nice little menu on it, which isn't on the tape version. There's the game. Oh, this logo's nice. Actually, it's using flashing colors or alternating colors to expand the color mixing that you would normally see on a like a CRT display, right? Because of persistence of the CRT display and the way that it treats color data and displays color data. By rapidly alternating the colors, you're basically using like expanded color mixing, which looks a bit better on a proper CRT. The CRT emulation on this version of Vice doesn't quite completely accurately reflect it, and it comes out even worse on a captured video. So the disk version has this nice little message appearing on screen. I don't know what it's doing when it's doing this. Maybe it's doing some calculation. Anyway, there's a little message which has this alternating green and light green thing going on, and it's just basically loading the data from disk at this point. So let's choose the demo option now. We go past this Synapse colourful logo again. It's quite a nice little thing to have on the disk menu. So we've got 3 demo games: Doughboy, Sentinel, and Zaxxon. Not the Sentinel, which is that 3D game where you have to wander around a 3D landscape. It's different. But yeah, this is, I think, Doughboy to begin with. Now, these games, if I remember rightly, they are self-playing demos. So I'm not playing it at this point. This is like a pre-recorded game input. But if we have a look at the memory events, we can already see that there was a whole bunch of stuff being read sequentially through memory. And that kind of makes me think that it was loading pre-recorded joystick data. So let's do a arranged watch load breakpoint for that next bank of memory locations, and there we go. It's hopped into this code here, which does a load indirect with f0, y. It then pushes the accumulator value, which is just loaded from the memory range. It looks like it's doing an increment of f0 and f1 and comparing f1 with the end of the recorded joystick data buffer. And then if it's reached the end of the recorded joystick data buffer, then it seems to loop around the code and reinitialize interrupts and stuff like that, and then jump to C000. But we don't want that to happen. We actually want to try and get this self-playing demo playable. So let's assemble some patch code at 5F8C. So instead of loading indirected from this memory block range, we'll load from DC00, which is, of course, one of the joystick port registers. So we'll load accumulator with DC00. I don't think that we want to do the push and then jump to where the PLA is. We'll just jump to, what is it, 5FBB, looking at the code there. So let's just do a jump to 5FBB. Let's copy this and put this into the debugging notes text file so that we can save the debugging notes for making this demo playable, hopefully. That's what that code looks like anyway, so let's just Doughboy, I think that's how it's spelt, right? Make playable, question mark. We'll see. I'm pretty confident that it is, but we'll just, double check. So let's delete the watched load breakpoint. That code seems to be shifting the bits out and then decoding them, right? So now you'll notice that if I move around the joystick now on the emulator, there you go. I can now play, I'm now playing this, what was a self-playing demo. Now I'm playing it. Not very well, of course. I haven't played this game in many, many, many years. It's an unusual style of game, isn't it? A very unusual topic for a game. Very unusual gameplay mechanics. But yeah, it doesn't like being reset, I don't think, but there we go. An unusual game demo, but one that you could have made playable. I don't think the full game is in there. But yeah, it's certainly something that you could have done to get more usage out of the game demo itself. Let's go into the next game demo now, which is available on this disc, and see if we can make that playable. So the next game demo is Sentinel, so let's pick Sentinel from the menu. So this is Sentinel, not the Sentinel. Looks a lot different, right, to the Sentinel, which is that 3D landscape game that you have to wander around absorbing trees and stuff, right, and rocks and things. Looking at the memory debug view for the memory reads and writes and execution, at first glance, I don't see anything which looks like sequential reads through memory for joystick controls going on in the game. So unfortunately, it doesn't look like it's going to be entirely easy to get this game demo playable. And to be honest, this game is a little bit confusing. There's a lot going on the screen, and it's like, what on earth is going on here? But yeah, I don't think it's going to be possible to easily make this game playable. So let's go on to the next game on the disc. So this is Zaxxon, which is an arcade game conversion. I don't know if it's official or not, but yeah. Let's see. So moving around. Well, in the memory debug view, there it is. There's a sequential read. So let's put a watch load ranged breakpoint on 8100 to 81FF. Actually, we can include the previous 256 bytes as well. There we go. Again, this is doing, oh look, it's doing a load indirect with F2, Y this time. There's some setup there of DC00 and DC01, which is setting up writes into the keyboard and joystick ports, I think, set up the keyboard for matrix row and column reading. But looking backwards through this code here, we don't want to do that. We just want to do, I think we just want to read, yeah, we just want to read the joystick at 5844. I think, well, that's the start of the joystick. Because look, it's basically hopping over this code, so it doesn't seem to be reading keys every frame. It doesn't seem to be reading recorded joystick presses every frame. It seems to be doing them every, 2 or 3 frames, maybe even 4 frames. So we'll just read the joystick every frame. I think that's probably the easiest way to do this, and we'll hop out over all of the end of the keyboard, at the end of the recorded joystick buffer recording and code, and the end of the joystick buffer code checks. We'll hop over all of those, and we'll just do a load with DC00 there, and then we'll just jump all the way over to 5869, which is where it seems to be processing. And now, if I move the I just crashed. Now, if I move the joystick around, I just got hit by a missile. I don't believe it. Let's try and avoid missiles and bullets and everything. There we go. I am now controlling what was a self-playing demo and flying around and shooting. So yeah, that was pretty easy to get 2 of the self-playing demos on this game disc playable. So that's how you kind of like, would in the old days try and make more use of self-playing demos by making them playable, and then at least you could enjoy them without actually having paid for them. which was great. You know, I don't think the full game, again, for Saxon is on this demo. I think it's just this level. And then I think it probably goes to the next part, which is flying around in space, right, with those spaceships and everywhere. Maybe this is a preview version of the game or something. Yeah, I crashed into the laser barrier. Well, that's not a surprise. But yeah, I think I've just about covered everything that I wanted to in this video for this version of Encounter on a tape and a disc. If you like these kind of deep technical dives into old Commodore 64 retro games, then please do consider liking or subscribing to this channel. I would like to thank all of the people that send me super thanks or donations. Your support is very much appreciated. You are my tank wandering around a landscape of towers to my mountains and clouds on the horizon. Anyway, thank you very much for watching. Take care, have a great day, evening, or night, wherever you are.